All right. Hopefully this isn't glitchy. All right, 9-4, day 1. We're going to develop 3 reduction formulas for the trig functions, and then in day 2 we're going to be using them. So I'm going to take you through a numerical one and give you the trick to start it out. Then we're going to redo it for the general case, and I want you to actually think about what's going on in each step. And then tomorrow you're going to do the other 3 functions that are parallel to these 3. So the goal is to develop a reduction formula. And I'll talk about what reduction formula means when we actually get through the process here. For the trig functions. Trig functions. All right, so we're going to start with cosine. And like I said, we're going to do a numerical example, then we're going to do the general case. So if we were going to integrate cosine, let's say to the 6th power. Okay, we can't do a power rule here because we would need the derivative of the inside, which is sine. I don't have a sine, I can't add a sine. So we're going to do this by parts. And all I've got to work with is cosine to the 6th. And remember, this has to be something we can take the antiderivative of. So I'm just going to make that cosine to the 1st, because I know how to do the antiderivative there. So that leaves cosine to the 5th here. So derivative, it's outside times inside, so the 5 comes down. I'm going to have cosine to the 1 less. And then the inside derivative is a negative sine. So I'll put the negative and the sine. Over here, I'm doing antiderivative. So antiderivative of cosine is sine. Okay, we're just going to do one iteration of this and get a reduced integral for a power of cosine. And you'll see what I mean in a minute. So it's multiply, add, minus the integral. So my first term is going to be, how do I write it here? Cosine to the 5th times sine. So I'm going to write this down. I'm going to start with this again, because this is going to reappear, I believe. Cosine to the 6th x dx equals u times v and then here I'll have a minus times a minus, that's going to be a plus 5 integral of, and I'm going to multiply, so I'll have cosine to the 4th, and then I'll have a sine squared. Okay, so what we're going to do now is use our Pythagorean identities, and I have them, and rewrite the sine squared. Pythagorean identity, sine squared would be 1 minus cosine squared. So that's going to give me all cosines in here. So keep that. I'm going to ditto that. I got 5. I keep the cosine to the 4th. Rewriting this as 1 minus cosine squared. Now I'm going to distribute to get rid of parentheses. So that'll give me cosine to the 4th minus cosine to the 6th And now what I want to do is, there's 2 separate terms here. I want to distribute the integral to both of them, because you can see I've got a cosine to the 6th over here, and I'm going to combine these. So all I'm doing is, instead of doing them individually, I am going to do them individually. So this would expand to 5 times the integral of cosine to the fourth minus the integral, 5 times the integral of cosine to the sixth. And they each have a dx. So all I did was take this one integral and break it into the two. So now what I can do is bring this term, it's a like term with the one that's over here, and I'll get rid of it by adding 5 integral of cosine to the sixth x dx to both sides. So here I have 1 integral of cosine to the sixth plus 5 more. That's going to give me 6 integrals of cosine to the sixth x dx equals, so I still have my first term that I'm going to write because I'm just about done. Plus, I've got 5 times the integral of cosine to the fourth x dx. And the last thing I've got to do is get rid of the 6 that's out here. So I'm going to multiply both of these terms by a 1/6. So I'm going to get rid of that. And I will have 1/6 cosine to the fifth x sine x dx. That'll be 5/6 integral of cosine to the fourth x dx. Okay, so this is called a reduction formula because I started with an integral of cosine to the sixth. Now I've done the work. Now I'm down to an integral with cosine to the fourth. So I've reduced this power, and I could repeat it again with the cosine to the fourth, the same process, and eventually we would get fully integrated. So we're going to be doing that tomorrow. Today is just to come up with the rule. So we did it with the numerical case of 6. Now I want to do it with the general case. If I call the 6 just any integer, n, it looks like the reduction formula would be, so this 1/6, this 6 down here does match my power I started with. It would be 1 over n. So this 5 power, how does it compare to what it started with? It looks like it's this number minus 1. And then we've got a sine x. Oops, x. Then we've got a sine x. This fraction, where does this fraction come from when I'm starting with the power of 6? Well, it looks like my numerator is n minus 1. My denominator is n. Cosine. And now this exponent looks like it's 2 smaller than the 6. So n minus 2. Okay, so by doing a numerical one, it looks like this is the reduction formula. We are now going to prove that this is the reduction formula. And what you have to do is follow every one of these steps carrying along an n in place of the 6. And you can do this. You're going to tell me you can't, but you can. So I'm going to pull this piece of paper off and follow it, and we'll try to go back and forth. So here's the real development of the reduction formula. So we want to develop cosine, the integral of cosine to the nth x dx. So I'm going to look right back at where I started. U dv. I know that under the dv I have to have cosine to the first. So that's what I'm going to put here. Cosine x. So that means if I'm stealing one of these, I've got one less. So to write that, that would just be cosine to the n minus 1. So no matter what n is, this exponent is now going to be 1 less because there's 1 over there. So now we know we do derivative here. You know the derivative rule is the exponent comes down. We multiply by the cosine to the 1 less, Well, if I've got n minus 1 and I subtract another 1, it's going to give me n minus 2. And then the inside derivative, remember the inside was just a cosine, so that's still just going to be sine. And then over here, you know this goes to sine. All right. So we're going to multiply. Negative integral. Keep this. So just take your time. Talk your way through it. So we multiply this term times this term, our diagonal. So that's cosine to the n minus 1, x times sine x. Then we've got, oh, I forgot the minus here, didn't I? Because the derivative of cosine is a negative sign. Almost made a mistake. Keeping going here. So we're going to multiply. We've got the negative times the, and I knew it was because I looked back here. I knew I didn't have the negative. So we're still multiplying. Negative times negative goes positive. I've got the integral of n minus 1 times cosine to the n minus 2 x sine squared. So I'm right here at my first line. So looking at what I did, I rewrote the sine squared with the Pythagorean identity. Everything else is just going to stay the same. And I put the 5 out in front where I've got the multiplier inside here. That doesn't overly matter, but I can pull that multiplier out in front. So cosine n minus 1x sine x stays the same. Taking out the n minus 1. Here, I'm going to keep the cosine to the n minus 2. And here we'll switch that out for 1 minus cosine squared. So this n minus 1 is a multiplier. Looking at what I did next, I did distribute that cosine. So I got rid of parentheses, so I'm going to do that. Just going to ditto that term. So here, cosine n minus 1, and cosine to the n minus 2 times 1 minus, and remember we add exponents here, so the n minus 2 plus 2 okay. Now I look back. After I distributed, then I just broke it up into the 2 separate integrals. I distributed the 5 integral to both of those. So, n minus 1 times the integral of cosine to the n minus 2x dx minus, now I take this and distribute it here. I'll have n minus 1 integral of cosine to the n x dx. And now looking, this last term should match what I started with. So, and I just add whatever number's out in front over to both sides. So, I'm going to bring this down. Oh, forgot my integral. So the integral of cosine to the nx dx, just bringing that down. Now I'm going to add n minus 1 of them. So adding n minus 1. So remember, there's like a 1 out here. So when I'm adding these like terms, I'm just adding the coefficients out in front. So the 1 plus n minus 1, the 1's cancel. I'm just going to get n. Integral of cosine to the n x dx equals, I'm now going to write down my first term because I'm just about done. Cosine to the n minus 1 plus, I got my second term, And then if you look, the last thing I did was divide by the coefficient that's out in front here. So I'm going to divide by n. So divide by n, divide by n, divide by n, and I'm going to be done. So I'll have 1/n here, 1 over n, cosine n minus 1x, sine x, plus n minus 1 over n, integral of cosine to the n minus 2 x dx. And if I check with what I thought it was going to turn out to be, I think it matches perfectly. Got the 1 over n's, cosine to the n minus 1x, sine x, plus perfect. So that's the development of it. So the trick was to pull off one cosine here, leave the rest of them over here. Each trig function is going to have a trick. So for homework, you're going to be doing the sine to the nth, and it's going to follow the same trick where you put sine over here and then one less over here. So there's your first one. Like I said, I'm going to do 3 with you. You're going to do 3, and that's going to be it. Then day 2, we're going to use the formulas. All right, I'm going to do, that goes there, tangent with you. So number 3, let's start with a numbered one. Tan to the 10th x dx. All right, so the trick here is not to do it by parts. What you want to do is break this up, pull off a tan squared, and if I do that, that will leave me with tan to the 8th. I don't know why I have that big gap there. And if you think about this, if you look at your blue sheet, the reason we're doing that is tangent's derivative is secant squared. Sorry, I'm not quite there yet. Now we're going to use Pythagorean identity to get secant squared introduced here. So Pythagoreans are here. Tan squared would be secant squared, and then subtract 1. So that's our next line. I got tan to the 8th. I'm going to rewrite that as secant squared minus 1. Then it's distribute. So I'll have tan to the 8th x secant squared x minus tan to the 8th x. Okay. Now what I'm going to do is see it as 2 separate integrals. So right now it's all of this dx. So now I'm going to break it apart into the integral of tan to the 8th x secant squared x minus the integral of tan to the 8th x dx. This term is going to be good to go because now I've got a reduced power of tangent, which is my goal. Remember, it's a reduction. I want to end up with an integral that has a lower power than what I started. I've just got to be able to integrate this, and I'll be good to go. So this is the one I was thinking of. The derivative of tangent is secant squared. So I can slide the secant squared over to the dx, throw it away, and do a power rule on the 8. So the antiderivative of this term is going to be 1/9 tan to the 9th x. That gets thrown away because it's the inside derivative, and then I've got my minus my reduced power of tan. And that's it. We've developed, hopefully, the reduction formula. So this one's a little quicker. So let's take a stab at what we think it would be for the general case of n. And then we'll develop it and see if we match. So looking at this, I am surmising that just comparing my 10 with the values that are here, this should be 1 over n minus 1, tan to the n minus 1, minus the integral of tan, and comparing 8 to the 10, that's 2 less, so n minus 2. So it took me 1, 2, 3, 4, 5 lines to get it with a number. It's going to take me 5 lines to get it for the general case. So let's put this to the side. We're going to see if we match it. So we're going to start out with tan to the nth, break it apart like this, and do these 5 steps. So here we go. Can we get this to be our final answer? So tan to the nth x dx. Okay, looking at the first line, the first thing I did was I pulled off a tan squared so that I could do a Pythagorean identity on the next line. So if I do that, if I pull off a tan squared, that means I have to reduce this by 2. So that will be tan to the n minus 2 x. All right, so that was our first line. Second line is to use the Pythagorean identity to get rid of the tan squared. So this is going to be identical. I have a tan squared. Now I've got secant squared x minus 1. The next thing I did was distribute to get rid of the parentheses. So I'll have tan to the n minus 2x secant squared x. That'll be it, and then minus tan to the n minus 2x, and that's both of these dx. And then after that, I just separated the two terms to their own antiderivatives. So I'm going to write this one as its own antiderivative. Okay, and this was going to stay exactly the same. This one I have to do the antiderivative of, and if I look, I did a power rule because I have the inside derivative, which is secant squared, attached to the dx and thrown away, added 1 times by reciprocal. So I'm going to attach this to the dx, throw that away. I'm going to add 1 here. That's going to give me n minus 2 plus 1 is going to give me an n minus 1. I got to multiply by its reciprocal. That got thrown away. And then I got tan to the n minus 2. And if you look at what our surmising was up here, I think we got it perfectly. Okay, so when you do cotangent, you're going to do the same thing. You're going to make it take off a cotangent squared, use a Pythagorean identity. It's all going to play out the exact same way, same 5 lines with cotangent. All right, and now the last one I'm going to do with you, I'm going to do cosecant. You're going to do secant for homework. So, we must be on 5. So let's start with a number. Let's try cosecant to the 8th x dx. Okay, this one is going to be done by parts. This one, the one that we can do the antiderivative of is to put a cosecant squared over here, because somebody's derivative is cosecant squared. Well, negative cosecant squared, so we'll have a negative cotangent here when we do it. that leaves 2 less, so that means cosecant to the 6th here. And now we're ready for one iteration. So that'll be 6 cosecant to the 5th x times the derivative of cosecant. The derivative of cosecant is a negative cosecant cotangent. So a negative cosecant cotangent. Okay, I'm going to have to simplify that because these two have to find each other. Over here, when I do antiderivative, so I ask myself, what has cosecant squared as its derivative? Well, that would be a negative cotangent, because this is a negative cosecant squared. So I need a negative cotangent here. Okay, so do know that these two terms come together. So this term, I'm going to write it underneath here. Negative 6, this will become a cosecant to the 6th x cotangent x. So here's my diagonal. And this would be my horizontal, but it's kind of down here. So plus, and then minus the integral. All right. So this one is where this is going to reappear over here, and we'll bring them over. So I'm going to take the time to write that down here. Cosecant to the 8th x dx. So my first multiplication is a negative cosecant to the 6th x cotangent x. And then this will be a negative times a negative. I got negative, negative, negative. So I've got the negative cotangent, the negative integral, and the negative 6. So we got another minus. Let's see, we will have the 6. I'll put it here. Cosecant to the 6th. And I'll have a cotangent squared. Okay, what we're going to do is swap this out with a Pythagorean identity. So I'm going to ditto that first term. We have a minus 6. Cosecant to the 6th is staying. Cotangent squared is, it'll be cosecant squared subtract 1. And you can see we've done the same thing every time with this. We're going to distribute and then break the two integrals apart. So we'll keep the negative 6. That'll be cosecant to the 8th. Oh, I'm back to what I started with over there. And then it'll be minus cosecant to the 6th. So now it's just a matter of breaking it apart, distributing this negative 6 to both of these and the integral to both of these. So we will have a negative 6 integral of cosecant to the 8th. So we'll be bringing that over to the other side. The negative 6 has to distribute to this negative here. So that means we will have plus 6 integral of cosecant to the 6th x dx. And that is exactly what we're looking for, a reduced power. So that term is done. Now I've just got to bring this over here and then divide by whatever coefficient I get. So we're going to add six integrals of cosecant to the 8th x dx. So doing that, we will have 7 integrals of cosecant to the 8th x dx equals, I've got my first term here, cosecant to the 6th x, cotangent x. This term is gone, plus 6 integrals of cosecant to the 6th x dx. And the last step is to divide by the 7. So I'm just going to cross that off, make this dividing by 7, so I have a negative 1/7. And this is going to be 6/7. And looks like we did okay. So we're going to surmise now what the integral of cosecant to the nth is. And so my n is an 8. This looks like negative 1 over n minus 1. Cosecant to the, looks like n minus 2, comparing 8 and 6. Cotangent x plus, this is n minus 2, this is n minus 1. Integral of cosecant to the n minus 2. Okay, I think, boy, I think I might leave that one and put it on day 2. I might just have you do 4 of them. Then that'll make, yeah, I'm going to do that. I'm going to put the secant one on the next day. I'm going to stop there. And, nope, actually I'm going to finish it up. Nope, I'm going to quit. I'm going to, okay, I know what I'm doing. I'm going to do the nth case as a refresher off of this one in the next set. I know what we're doing. Okay, so we're good. So you're only going to have 4 problems tomorrow instead of 6. All right, calling that quits.